So this is part 2 of week 2, and this is dealing with stars, how we classify them and their life cycles. This is called a hertzsprungrussell diagram, and this kind of shows a couple of different things if you look at the different axes. It shows how bright stars are. That's their luminosity. It shows the temperature of the stars. And then also shows their size relative to other stars as well. And then on the bottom, it has kind of how we classify them. Now, there's this main sequence here. This is where stars spend 90% of their lives. So it is ranked according to temperature or luminosity. Our sun is kind of around here somewhere, where it has a luminosity of 1 and a temperature around 5,400. So our sun is probably somewhere around there when it comes to stars that we're most familiar with. Now, through the life cycle of these stars, they burn different elements. And when stars are relatively young, what they mostly do is they, through fusion, so they fuse hydrogen. So they fuse hydrogen nuclei, and under very immense temperatures and pressures, they fuse those into helium. And that is kind of the main fuel source of these different suns, is they're forging hydrogen to make helium, and in the process they produce all of this energy. Now, as time goes on, they start to run out of hydrogen, and so they start to fuse helium, and then as time goes on, then they start to form larger elements together until eventually they get to iron and die. But based off of kind of the size and what elements that they're actually fusing, we have these different colors. These giants and supergiants here are typically stars that have very large radii, and they've exhausted the hydrogen fuel in their cores and have started to burn helium and other elements, and so we get these very large stars up there. These white dwarfs down here, so this region, this is kind of the final evolutionary stage of low to medium mass stars, and they're kind of found down there. They're very hot, but they have low luminosities because they're pretty small. So we kind of have these different parts of this diagram where we go back there, O to M. Class O ones are up here. So these are very bright, and they are very hot, and they are also very large. And then we go down here to some of these ones, which are fairly dim and relatively smaller and colder. So kind of the blue, white hot ones are burning very hot. These different stars, and also how we end up with some of the stars live. Now, on the bottom axes, there's a classification there, and so they use temperature and color in order to classify these stars. You'll notice how they classify them. So class O all the way to class M. Now, there is a mnemonic to help remember that. They go O, B, A, F, G, K, M in order of classification. O, be a fine girl, kiss me is one that maybe is easy to remember. You can come up with whatever you want with those letters. But that's kind of how we classify them, according to their temperature and also according to their color. And they're very large, and then they change color as they get different cooler. Now, based off of the size of the star, it can undergo a couple of different life cycles. Average stars like ours, eventually they burn up all of the hydrogen, helium, they start to get larger, and they start to fuse together larger elements. Once they do that, eventually they'll die and might become a white dwarf. Larger stars, so as they get bigger, they start to fuse some of these things into iron, but then they actually implode on themselves in supernova. A supernova is where we get some of these other elements that are larger than iron up to uranium. So those elements all come from supernovas, where as this star dies, it implodes on itself and then it explodes outwards. In that process, it has a lot of energy to fuse together some of these larger elements. Now, based off the size of that body, we can end up with a neutron star, or if it's bigger, we end up with a black hole. So kind of those are the three main products, like white dwarfs, neutron stars, or black holes, based off of kind of what type of star we start with and where it is in its life cycle that we want to be concerned about. So in stuff like our sun, so here in the low mass stage, it's fusing together hydrogen. So hydrogen's being fused together to make helium. Can have different forms of hydrogen. Then this red giant stage, it's starting to fuse together larger elements. So it starts to expand, fuses together larger elements, and then it dies, and we end up with a white dwarf, which is kind of like a ghost of what it once was. If we have something that goes, so we have an intermediate mass star, it undergoes some of those same fusions, but then it undergoes the supernova phase. So when we talk about stars, it's always kind of a balance of two forces. They're so massive and there's so much mass that there's the force of gravity acting on all those things, pulling them in. But then there's also this force from the fusion that's pushing it out. And so it stays kind of relatively that size. What happens when it undergoes supernova is now the force of gravity wins. So as I start to run out of stuff to fuse, now that star actually implodes on itself. So it implodes, and then when it reaches that iron core, it rebounds and then goes supernova. It's kind of how a supernova happens. What we're left with at the core there, if we have a certain mass, we have a neutron star then, is what will be left there. It's extremely dense. And I would recommend, if you're interested in that, choose that as one of your options in the assignment. But it's extremely dense and has a lot of super interesting properties. Now, once that star goes supernova, if there is more mass in the center here, then we can end up with a black hole. And I know Sam doesn't believe in these. I think I learned that in Physics 20. But we can end up with a black hole if we have enough mass. And typically when you see these black holes in movies, what you do see is the event horizon. So you don't actually see the inside of a black hole, because in order for anything to get out there, it needs to be traveling faster than the speed of light, which is c. And there's nothing in the universe that can actually do that. So there's this region that you can't actually see. That's the black part of the black hole. What you can see is this event horizon. So these are things around the outside of the black hole which are moving very fast because they're kind of being pulled into the black hole. So by the time they get there, they're accelerating a bunch. And because they're because it's accelerating charge, it's giving off stuff like X-rays, which we can detect. It's giving off kind of other forms of light that we can see. That's the event horizon. So that's the point where stuff can still get out. But inside that event horizon, everything is trapped, and you can only escape that if you're going faster than the speed of light. And again, that if you're interested in black holes, I would suggest that you choose kind of that option for your assignment this week. So that's just